In case you're wondering why I have those little stars up there, it's just a little test pattern to make sure that the camera can see the board. It has a very hard time focusing on the board because it's all white. So I put these little things up there so it can find a place to focus. So now, what we're going to do is take a look at projectile motion. All right, and we're going to take a look at a specific problem called the monkey and the hunter. I'm not going to get into that too much. I'm going to show you a video on how it works. I'm going to give you the setup for it, ask you to make a prediction, and then you can go watch the video. So now, let's take a look at what we talked about last year, which was the 6 equations of motion. Last year, we had this setup. Okay, we said that x was equal to my initial velocity in the x times time plus x0. My velocity in the x is equal to my initial velocity in the x, because that doesn't change, and that's because my acceleration in the x is equal to 0. My y was equal to 1/2 gt squared. Well, let's just write it as, yeah, we'll say gt squared, and we have to put a negative in there. Plus v0y times time plus y0. My velocity in the y as a function of time was equal to negative gt plus v0y, and my acceleration in the y was equal to negative g, which is equal to negative 9.8 meters per second squared. We're not going to make it 9.81. 9.8 works just fine. Okay? It's really 9.806 for most places near Earth's surface, I think, specifically at this latitude and longitude with anomalies and everything else like that. I think they estimate it reasonably well at 9.806 for this area. That's neither here nor there. But now, we can rewrite this now with some of the things that we know. Okay? We can say that my position vector is going to equal, and the x direction is going to be, and assuming that x0 is 0, because we always said, we pretty much always do that, we're just going to say it's v0x times t, so I can almost always set that to v0. y0 is not as easy to set to 0, because it can land at a different height. At time t equals 0, we almost always set this equal to 0. So that's going to be I hat plus negative 1/2 gt squared plus v0y times time plus y0, and that's going to be j hat. So our 6 equations of motion we can get down to 3, and we can just take the derivatives to figure out what the rest of them are. Once you know these two, okay, you put it into one equation, and then velocity is a function of time. Well, guess what? If you take the derivative of this, you get v0x I hat. Take the derivative of this, oh, look at that. You get that. Plus negative gt plus v0y j hat. Okay, take the derivative. This is 0, this is v0y, this is gt. Acceleration is a function of time. There is no acceleration in the x direction. Okay, this drops off, so we're just left with negative g. Okay. So what we did last year was really putting this into I, j, and k, but we didn't put it all together in one. It's also the same idea as parametric equations that you might see in your math class, okay, where you have x is a function of time, y is a function of time, z is a function of time. It all ties together. It is all the same thing. But now we can put this all together in one nice little setup there. Now, there's all sorts of stuff about that we can take a look at here. As far as projectile motion analyzed, when they go through the equation of path, they talk about the horizontal range and that sort of thing. I don't find that terribly interesting to come up with an equation. It might be something that you just take note of, and if, especially the horizontal range, you know, it might pop up on the multiple choice section of the AP test. So you might want to just take note of it. I'm not really going to ask you a question where I ask you specifically what is the range equal to, but this is going to be V0 squared over 2G times, over G. Times the sine of 2 theta. Okay? I'm not big into memorizing equations, but it's not necessarily a bad thing to know what an equation is. We can take a look at a sample problem real quick, just to figure out how all this stuff works. It's not going to be a short problem to go through. Projectile motion just is a tedious little thing that you just have to go through. Okay, so let's just take a look at a sample problem here. I'm not going to do one that you guys are given, so this is going to be in 4-6. By the way, I should mention, okay, projectile motion is a special case of motion where we specifically have the acceleration is equal to negative 9.8 meters per second squared. The only force that acts on the object is gravity. Okay, we are going to neglect air resistance. We are neglecting whether there are any other forces like an electromagnetic force or friction or anything else like that. All we're going to do is take a look at gravity, and it is a very important case. We will take a look at some of the simpler ways to take some of the simpler air resistance problems, but we're going to hold off on that for a little while. You guys are going to learn about differential equations in your calc class, and I'm going to try to marry the two together this year. So anyway, just take a look at a projectile motion problem. A certain airplane, this is, let's see, 1134. Okay. So let's take a look at number 23 in your book. Okay, there's a picture that goes along with it. A certain airplane has a speed of 290 kilometers per hour and is diving at an angle of 30 degrees below the horizontal when the pilot releases a radar decoy. Okay, so now, what we have here, and we can use 6 equations of motion, or we can set it up into this, oh, by the way, R is a vector. Or we can set it up as a, in the full vector form. I really don't care. Whichever method you feel more comfortable with, by all means do it. So now we have an airplane, okay, that's diving at an angle of 30 degrees. Let me make that airplane dive a little bit more here. It's diving here at an angle of 30 degrees. Okay. I can make that airplane a different color just so it shows up a little bit better. Okay. So my airplane is diving at an angle of 30 degrees below the horizontal. It's going 290 kilometers per hour. So the speed is equal to 290 kilometers per hour. it releases a radar decoy. The horizontal distance between the release point and the point where the decoy strikes the ground is 700 meters. Okay, so here's the ground. So here's the decoy as it's being released. Okay, so the decoy is also going 290 kilometers per hour at 30 degrees below the horizontal initially. Okay, it's going to follow a path where it goes like this. It's not going to go straight down. Okay, it's going to start curving downward. Okay, the distance here, and this is where reading is a very important part. We have to be able to pick out what all the terms mean. Okay, this is 700 meters, I believe. We want to know the time that decoy is in the air, and how high was the release point. So I'll call this distance right here y. Part B, we want to know what y is equal to. Okay. Well now, first things first, I want to get into units that I'm a little bit more familiar with or that are consistent. I have kilometers here, I have meters here. They don't match, okay? Let's convert the kilometers per hour to meters per second. So now, I know that V is equal to 290 kilometers per hour. Now, I know that there are, in 1 hour, there are 3,600 seconds. Okay, 60 seconds per minute, 60 minutes per hour. I know also that I want to get rid of kilometers, and that there are 1,000 meters per kilometer. Now, once you get familiar with this, you can just take your velocity. It's going to, whenever you have to convert from kilometers per hour to meters per second, you're just going to divide 1,000 divided by 3,600, and you're going to wind up with dividing by 3.6. So if you're familiar with that, you can certainly do that, but get familiar with how that comes about. So that's 80.56 meters per second. Now, so that's my velocity. Now that's my velocity in both the y direction and the x direction. So how can I want to know, okay, I don't know this height, but I know how far across this is. So if I look at the x direction, x is equal to v0x times the time. I know x in the air is going to be 700. I know I'm solving for t air. Okay? So I'm solving for this. I can get that pretty easily. Okay? My Vx is going to equal, my V0x is going to equal my V0, I should write this as V0, times the cosine of 30 degrees. So V0x is equal to, and it's not negative because it's going in the positive x direction. So I'm just going to multiply that by cosine of 30 degrees, and I got 69.76 meters per second. So now, I want to know what the time is in the air, so I can say that my x final is V0x times t air. So my x final is 700 meters is equal to 69.76 meters per second. Keep all the digits in there, by the way, in your calculator, so you'd have 10 digits or whatever, times t air. Divide both sides by 69.76, and I get an answer of my t air is equal to 10.03 seconds. Okay, so that's the time in the air. I want to know what the initial height is here. Okay. Now there's a couple different ways I can set this up. All right. I know that this is going to fall for 10.03 seconds. If I look at my y equation of motion, okay, I'm going to say that y is equal to, and you can use symmetry and everything else like that too. That's perfectly fine. You can say down is positive. For simplest case, for first case, I'm just going to set it up the way that we're used to, with up being positive and down being negative. But that's probably not the easiest way to look at it in this case. So now, this is going to be negative 1/2 gt squared plus v0y times time plus y0. Well, here's the thing. Okay, I know g. I can get v0y okay. And I know y at a particular time. Okay, g and v0y are constants. So is y0, but I'm solving for y0. And you say, well, I've got two more unknowns here, but I don't know what y is at all times. I could say any time t, but at one particular moment in time, I know what y is equal to. When this is on the ground, okay? When this hits the ground, so y equals 0, I know that that time is the time in the air, which is 10.03 seconds. So let's go ahead and solve for v0y. v0y is going to equal, and we're saying up is positive, v0y is going to equal negative, because this is pointed down, that 80.56 meters per second times the sine of 30 degrees. So my v0y will equal negative 40.28 meters per second. Okay. So now, at time t equals 10.03 seconds, okay, I can solve for y0. Okay, doing the algebra. And I challenge you, by the way, right now, to solve for y0 and see if you come up with the same thing I do. If not, keep working on it. So hit pause. All right, so hopefully you've solved for y0 now. y0 will equal y, okay, move this over, plus 1/2 gt squared. Move this over and you get minus v0y times time. And this is specifically, we're going to solve for t air. So y0 is equal to 0 plus 1/2 9.8 t air, which is the 10.03. It's going to be seconds squared. That's meters per second squared. Start worrying about your units. Minus v0y, which is the 40.28 meters per second, times 10.03 seconds. So now y0 is equal to let's see where the mistake is here. So now, I knew I forgot that answer wasn't working for me. You put the minus right there. Okay, I did forget the minus sign. So now I have 1/2. And I wind up with 897 meters. Okay, so yes, minus signs can make a very big difference. I forgot the minus sign here, okay, putting it in right there, and I wind up with 897 meters. All right, that problem's not too bad, little calculator mistakes, but you should get a sense too. If something is, if I just drop, here's where I was able to figure out where I made a mistake. If I drop something for 10 seconds, okay, just looking at 1/2 at squared, where it's not being thrown down on top of it, Okay, if I threw it down for 10 seconds, okay, that's 10, that's 100. G is about 10, so that's 1,000. Multiplied by a half, that's 500. So I knew it had to be greater than 500 meters high, because this is just telling me that it's going down on top of it. Okay, so it had to be an even greater distance. Okay, now a bit of a shortcut we can take is to take a look at let's say down's positive. Okay, so now if down is positive, all right, I can say that starts falling from 0 and it's going to fall down to here. Okay, so I'm going to set y0 equal to 0. So in that case, I have y is equal to negative 1/2 gt squared plus v0y times time. Now y final, which is equal to 0, will equal, y final, that's what I did before, y final, which is what I'm looking for, will equal, and that's positive, by the way, because I'm saying down is positive, 1/2, 9.8 meters per second squared, times t squared, which is 10.03 seconds squared, plus, now down is positive, so I'm going to say plus 40.28 meters per second, times the 10.03 seconds. And, oh, look, by the way, that's exactly what we wind up with here without having to go through some different rigmarole. Okay, so that y final should definitely still equal 897 meters. Okay. Last thing I want to talk about here with projectile motion is the hunter and the gun. Okay, the hunter and the monkey. So in that case, and I'm not going to actually work it out. I'm going to leave that as an exercise to the student. And you'll see that a lot in your textbooks next year. Okay? So now I have a hunter here, laying prostrate, the gun in his hand, the rifle, okay, and I've got a monkey here, guess it's a poacher or something like that, hanging from a branch. Now, here's the point of this problem, okay? The point of this problem is that at the moment that the gun is fired, the monkey gets spooked and he drops out of the tree. So what happens is, we want to know if this monkey releases at the moment that the trigger is fired. We want to know where we're supposed to aim it. Should we aim directly at the monkey? Knowing that, well, the bullet and the monkey are both affected by gravity. Should I aim a little bit lower? Okay. Should I aim, say, down here? Knowing that the bullet is going to fire off, it's not going to be in the air for all that long. So it's really not going to be affected by gravity. You have to aim a little bit lower for the monkey. Okay? Or the monkey, okay, the bullet moving so fast is more affected by gravity. Do I have to aim higher? Do I have to aim up here? So do I aim above the monkey, at the monkey, or below the monkey in order to hit that monkey? All right? Now, I'm not going to analyze it mathematically for you right now, but I want you to pause this video and watch the video that's just below the MIT video. So hit pause right now. Okay, so now what happened in that video, okay, The monkey falls. At the same time, this bullet is fired off. It's also affected by gravity. Okay? So now the two of them will met right about there because this is deflecting, this is going off its path and it's going straight up. The monkey is going straight down. They're equally affected by gravity as they fall, so you aim directly at the monkey and it's going to fall and it will hit the monkey as it falls. All right.